This is the makeup lab for Chemical Kinetics Week 1. What we're going to do is run through the first couple of pages of the lab handout in your lab manual called Chemical Kinetics Week 1. The first idea that we need to talk about is how reactions happen on the particle level and the different factors that can affect how quickly they go. So up here in this box is two particles that we're going to shoot at each other. And this is the whole mental model we use to think about reactions, that in order for a reaction to happen, two particles have to hit each other, just like that. So you can see the yellow particle is hitting the purple one, and we're making some products. There are different factors that affect whether or not this reaction is going to be successful. The first factor is how much kinetic energy the particles have, whether the yellow particle is hitting the other with enough energy for the reaction to happen. So you might have seen a graph sort of like this, where we have the energy of the reactants and then the products, and we have to overcome an energy barrier in order to make those products. We call that activation energy. Another factor that affects whether or not a reaction will be successful is how frequently particles will collide. So if I have more particles in there, that's going to increase the likelihood that they're going to hit each other. If I change that, that will affect the rate of the reaction. So this mental model that we use is known as collision theory. Oops, switch this. Okay. So reactions depend on particles colliding. A and BC. A needs to hit B to make AB, and then C by itself. So how quickly this reaction takes place depends on three factors. It depends on how frequently the particles hit each other. We can adjust that by changing how many particles are present. It also depends on whether or not they have enough kinetic energy to overcome that barrier to make the products, that activation energy barrier. And a final factor that is important is the 3D orientation with which the particles collide with each other. So for example, if we have particle A hitting BC like this, that would be preferred over A hitting CB, where the particle is just flipped around. So this is going to tend to give us a successful reaction, and this is not. So this mental model of thinking about reactions in terms of them colliding with each other is known collectively as collision theory. So in the lab, what we would have done, and this is the first page in the lab manual, is we would have carried out a reaction a series of times and played around with some factors to see what affects the rate of the reaction. So the reaction today would have been hydrogen peroxide decomposing. So here is that reaction here. Hydrogen peroxide is H2O2, and what happens is two particles of H2O2 hit each other and they form these products here. We make two particles of water and we make one particle of oxygen gas. Well, what we would do in the lab is we would carry out the reaction in a flask. We would collect the oxygen, and as the reaction proceeds, the amount of oxygen is going to increase, so the pressure is going to increase as well. So if we hook this up to a pressure sensor attached to the LabQuest, we're going to get a graph that looks like this. If we graph pressure on the y-axis versus time on the x-axis, we get this linear section right here. So this is showing us how the pressure is changing over time. And that's one way that we can measure the rate of the reaction. For this particular sensor, it measures in kilopascals and the time is in seconds. So the rate of the reaction can be expressed in terms of kilopascals per second. So down here, we're going to pretend we carried out this reaction once. And let's say that as a class, we got the following rate, 0.046. So that means that every second that went by, the pressure went up by 0.046 kilopascals. That is going to be our baseline rate. Further down on the page, we have this big table down here. So here's our baseline rate from before, 0.046. And now we're going to tinker around with some of the variables. We're going to change the temperature. We're going to cut the hydrogen peroxide in half. We're going to double it. We're going to add more catalyst. And then finally, we're going to increase the temperature. So let's say we get these sample values. Lower temperature, 0.022, 0.018, and so on. Now what we can do is compare these values to the baseline rate. So for lower temperature, as you'd expect, if you carry out a reaction at a lower temperature, you're going to have a reaction happening at a slower rate. If you think about collision theory and why that is, well, what happens when you have a lower temperature is those particles have lower kinetic energy. And on top of that, the particles are not going to collide as frequently with each other. So if you'd like to go through the rest of these and see if you can use this collision theory idea to explain why the rate of the reaction becomes either faster or slower than the baseline. And that's an important idea to understand. What is it about the particles in terms of their collision that's causing this number to change the way that it does? On to the next page. This is page 2. There's this table here. What this table is going to look at is specifically the effect of changing the amount of hydrogen peroxide on the rate. And from this, we're going to derive an equation. So we have the rate again. We have kPa per second. Here's the baseline rate from before. Let's say we carry out the reaction again, and we get this, 0.092. The only difference is that rather than using this much H2O2, we're going to use double. The third one, let's say we triple the amount of H2O2, and we get the following rate right here. So going from 0.15 to 0.3 molarity, that factor increase is double. We're doubling the amount of hydrogen peroxide that's present in a given volume of solution. Going from 0.15 to 0.45, that's tripling the concentration of the solution. So now what we're going to look at is the relationship between this column right here, the rate, and the concentration. One way to see what kind of a relationship we've got is to take the rate and divide it by the concentration and see if we get a constant. So the unit for this is going to be the unit of the rate divided by the unit of concentration, specifically kPa per second per molarity. So if we divide 0.046 by 0.15, what we get is 0.31. If we divide 0.092 by 0.30, we get 0.31 again. And finally, if we divide 0.138 by 0.45, once again, we get 0.31. We are getting a constant. So we can derive an equation from this. And that's what we're going to do below here. Okay. So we know that if we take the rate of the reaction, we divide it by the concentration of H2O2, we get ourselves a constant. The letter that we usually use to represent the constant is the letter K. And because we're looking at rates, we call this the rate constant. So this equation here that shows how the rate of the reaction depends on the concentration of the reactant is called a rate law. Now, it isn't always as simple as this, meaning you don't always get a constant when you divide the rate by the concentration. You have to do a little bit more math in order to get yourself a constant. So that's what this next example is going to show. So further down on the page, on page 2, we have the sample data. This is just made up numbers. And what you can see is if you do the same operation that we did before, rate divided by concentration, for this first row right here, 0.3 over 0.1, that's 3. 0.12 over 0.2, that's 6, and so on. So what this is showing is that we are not getting a constant, just like we did before. So does this produce a constant? The answer is no. But you can see that there's something going on here. There's some kind of a mathematical relationship going on. And what we actually have to do in order to get a constant, and this is on the next page, is to take the concentration and square it first. So let's see. 0.1 squared is 0.01. 0.2 squared, 0.04. 0.16 and 0.36. Now, if we take the rate of the reaction and divide it by the concentration, for the first row, we get 30. For the second row, we get 30. Now we're getting our constant. So the equation that we can derive from this is going to be rate of reaction divided by concentration of H2O2 squared equals our rate constant. That is just how we're going to get the rate constant. So what happens here is sometimes reactions have an effect on the amount depends on the rate in terms of an exponent. So the name for this exponent is called a reaction order. What's really good to know is that these reaction orders are going to be small whole numbers, and usually what we see is the number being either 1, 2, or sometimes 0. What that means is if the order right here is 1, it just simply means that these two are directly proportional, meaning that if you double the concentration, you're going to double the rate. If this is 2, that means that if you double the concentration, you're actually going to quadruple the rate. Finally, if this is 0, anything to the 0 power is 1. So that means that no matter what the concentration is here, it's not going to affect the rate. All right, so now further down this page, there is an example. So on your handout, let me pull that up. Go. So further down this page, you have this. It's an example that will show you mathematically how we determine the value of the rate constant given experimental data. And that's what's important to know about these types of calculations is in order to get a rate law and determine the values of the reaction orders, you have to actually carry out the reaction. So what this is going to do is walk you through an example, and then for the follow-up questions are simply going to be you using you following an example like that. So the follow-up questions is this page right here, and again, it's just following the example that's on this page right here. Hopefully you won't find it too difficult, but please let me know if you have any questions. Otherwise, these follow-up questions will be due the next time we meet for lab, which will actually be after spring break. That's about it. Again, please let me know if you have any questions. Have a great day.